Welcome back to module 4. In this module we have presented Hilbert space, which is a mathematical space, and we have said that all quantum mechanically acceptable wave function must live in the Hilbert space, and any operator we select to perform anything in quantum mechanics that should not take the wave function out of Hilbert space. It should keep things in the Hilbert space. So, this criteria we have presented, and we have shown the meaning of adjoint of an operator, and we have seen that sometimes for an operator A, in many occasions we have seen that A is not equal to its adjoint, such as d dx, derivative operator, they are not equal. But sometimes A can be equal to its own adjoint, such as x operator, such as I d dx operator. For these two operators, this is valid. And when this is valid, it is called self adjoint, and a self adjoint operator is called Hermitian operator. And we will see that already we have noticed that this operator d dx operator has taken a function out of the Hilbert space, and here we are seeing that their adjoint is not equal to its own operator. So, this kind of operator cannot be acceptable in the quantum mechanics. In order to use an operator in quantum mechanics, it has to be Hermitian operator, which means that its adjoint would be always equal to its own operator. So, this is something which is a requirement for quantum mechanics. All quantum mechanical operators are Hermitian operators. All quantum mechanical operators are Hermitian operator, which means that it is self adjoint, it is equal to its own adjoint. And what we will prove here now, then if A is an Hermitian operator, then A acting on psi giving me, this is called eigenvalue equation, then lambda is going to be always real. What it suggests that an important property of Hermitian operator is that the eigenvalue of a Hermitian operator is real. This is another one property of the Hermitian operator. So, I have mentioned that in quantum mechanics any operator cannot be used, this kind of operator cannot be used, only self adjoint operators can be used, which is Hermitian operator. The moment I use Hermitian operator in quantum mechanics, it gives me a direct consequence that eigenvalue of that operator is going to be always real. So, let us prove that eigenvalue of Hermitian operator would be real, minus infinity to plus infinity. I am going to find out this integration. This is nothing but A acting on psi, which is nothing but lambda minus infinity to plus infinity, psi star psi, which is lambda. And I have to find out now minus infinity to plus infinity, A dagger psi whole star psi dx. This is nothing but, now because A is Hermitian operator, its A dagger would be equal to A, which means I have A acting on psi star psi dx. Now A acting on psi is lambda, so I get lambda star minus infinity to plus infinity psi star psi dx, which is now psi star. Here we are assuming that psi is normalized, which means is living in Hilbert space. It is normalized, and that's why we can write down this psi star. So we have seen that in order to be an Hermitian operator, it has to be self-adjoint, which means that these two integral would be equal. These two integral, and in order to be equal, I need to have lambda to be lambda star, and this is possible only when lambda is real. A physical quantity can only be equal to its complex conjugate when lambda is real. For complex value, let us say IB is a complex value, can never be equal to its complex conjugate, because complex conjugate is going to be minus IB. So lambda cannot be a complex number, lambda has to be a real number, which proves the fact that eigenvalue of Hermitian operator is going to be always real. So in quantum mechanics, all the acceptable operators which I will use, which they are going to be Hermitian operator, and whenever that Hermitian operator, acceptable operator in quantum mechanics, when be acting on the wave function, I will get the real eigenvalue. That's the bottom line of this analysis. Next we will move to unitary operator. How do we define unitary operator? An operator U is unitary if inverse of that operator is equal to its adjoint. So when inverse is equal to adjoint, when if this is equal, we call it Hermitian operator. This is Hermitian operator. But when its inverse is equal to its adjoint, then it is called unitary operator. An important property of unitary operator is that if A is Hermitian operator, then e to the power IA is going to be an unitary operator. This is the property. If A is Hermitian operator, then e to the power IA would be unitary operator. We can prove that e to the power IA, now exponential and operator, and then minus 1. First I have to find out the inverse of the operator. So this is the operator we are talking about. This is U. Now we have to first check the inverse of that operator. Inverse of the operator is going to be e to the power minus IA, which can be written as following Taylor series expansion: IA plus minus IA whole square divided by 2 factorial plus many other terms. This is Taylor series expansion we are using, which is nothing but 1 plus IA dagger plus IA dagger whole square divided by 2, and because A is Hermitian operator, because this is true for this is Hermitian operator, A is Hermitian operator, I can write down this nothing but 1 plus IA plus IA whole square 2 plus, because Hermitian operator, in order to be Hermitian operator, this should be equal, which means that this one is nothing but e to the power IA dagger. So we have proved that unitary operator inverse is equal to its dagger. That's why this is unitary operator. So it's an interesting property. If A is Hermitian operator, so exponential of that operator, exponential of an Hermitian operator, exponential of an complex exponential, not any exponential, complex exponential of an Hermitian operator is a unitary operator. We'll move forward. There are many properties of the operators and the common algebra of operators we are going over. Commutators of two operators are defined by the sign A comma B within bracket B. It is given by AB minus BA. This difference is called the commutator. And if A and B commute, then AB equals 0, which means AB equals BA. Doesn't matter which way it is acting. So I can have AB acting on psi equals BA acting on psi. The order doesn't matter whether B will be acting first or A would be acting first. That order doesn't matter if they commute. But if they are not commuting, if this is not 0, then order will matter. So AB psi will not be equal to BA psi. Who will talk to psi first? That will matter if they are not commuting. We'll go to this exponential function of an operator, which we have already seen how to express exponential function of an operator. If it is e to the power A, then we can use Taylor series expansion. E to the power A equals, this should be 1, but to preserve the notation of the operator, we are giving the cap, A cap. A cap is nothing but 1 multiplying by 1. So 1 plus A plus A square by 2 plus A cube by 3 factorial, and this is the way we have to expand. And what does it mean by this power? A square is nothing but A multiplied by A. So if it is acting on psi, so first A will act on psi, then again A will act on the entire component. So that's the way we move forward with this power law of the operator. Often in time dependent quantum mechanics, exponential operator is used to move initial wave function in time and space. For example, e to the power, this is something which we'll notice very soon, e to the power I h t by h cut represents time propagator. and that's why it is called time evolution operator. Why it is called time evolution operator, we'll find out. But one thing is clear, because H, we know that it is Hamiltonian operator, is also an Hermitian operator. So if H is Hermitian operator, in the previous slide we have seen that if H is Hermitian operator, this whole complex function is going to be an unitary operator. So this time propagator is an unitary operator, unitary operator in quantum mechanics. Now, why it is time evolution operator? We'll prove this. It is time evolution operator because if we know psi x0, a particle represented by the wave function, initial wave function, then I will be able to find out psi xt at a time t, what would be the wave function of that particle. That can be found by employing this time evolution operator on it. So from initial wave function I can get the final wave function with the help of this time evolution operator. Now we'll prove how this time evolution operator is giving us this equation. This is something which we'll prove right now. We'll use Taylor series expansion and we'll check this first. So the equation which I have given here is that psi xt is equal to e to the power minus I ht by h cut psi x0. So this is something which we have to prove using time dependent Schrodinger equation. And if we can prove, then it will show that this operator, which is unitary operator, can be used to move the wave function from 0.0 time to other time, and we'll be able to find out the wave function at time t. So what we'll do first, on the left hand side psi x t, we can expand in the Taylor series expansion as psi x0 plus d dt of psi xt at t equals 0 plus 1 by 2 factorial d2 psi dx dt2 at t equals 0. So near t equals 0, the values, the derivatives are known, we'll say, and I can write down t square plus like this way. So this is your left hand side I have. On the other hand, right hand side I have e to the power minus I ht by h cut psi x0 which can be rewritten as e to the power ht by I h cut psi x0, which can be written as 1 plus ht by I h cut plus 1 by 2 ht by IH cut whole square. So this is the operator acting on psi x0. Now time dependent Schrodinger equation is giving me IH cut d dt psi xt equals h psi xt. Now these should be partial derivatives because x is depends on time and space, and this should be also partial derivative. So what I get here is that there is an equivalent from TDSE. I can get an equivalent relationship. IH cut dt is equivalent to H operator, and this equivalent relation we will insert here. So if we do that, then what I get is following. So from this step I get e to the power minus I ht by h cut psi x0 is going to be now psi x0 plus psi xt dt at t equals 0 t plus 1 by 2 factorial psi xt dt at t equals 0 t square, like this. What we see, this is right hand side. The left hand side and the right hand sides are equal, and because it is equal, we can say that psi xt equals e to the power minus I ht by h cut psi x0. So this is obtained with the help of TDSE. So one can say that this is a solution of TDSE. So time evolution operator is a solution of the TDSE, and we will very extensively use this time evolution operator in propagating the wave function. As if I know the wave function at t equals 0 time, I will be able to get to know the wave function at any time depending on this time evolution operator. So with this idea, so far we have described different properties of the wave function and the operator which can be used in quantum mechanics, and we have reviewed several general properties of the quantum mechanically acceptable wave function and operators, which are two key constituents of quantum mechanics, and we have defined necessary linear algebra terminologies using simple analytical mathematics such as integration, differentiation, exponentiation. All this we have used, Taylor series expansion. So we have used simple analytical mathematics such as integration, all these things, or integration, differentiation, and we have defined the properties of the wave function and the operator. While this analytical approach helps develop the basic theoretical framework needed to understand the quantum mechanically acceptable wave function space and operator space in details, I have already pointed out earlier that our ultimate target in this module is to prepare the platform for numerical implementation of the wave function and the operator, and that will give birth to this basis set approach to quantum mechanics. and we will look at how this can be done. So far whatever we have studied has prepared the linear algebra connection, the background or the realization of the connection between linear algebra and quantum mechanics. Now we are going to represent the key constituents of quantum mechanics, which is wave function and the operator psi and a. Both needs to be represented in the matrix form with the help of all the properties of linear algebra, and we will see how to do that. So here first we will do one comparison between a vector and a wave function. What is the connection between them? In three-dimensional space, a vector is often represented by its components with respect to the xyz axis. For simplicity, here consider a vector, two-dimensional space you consider, and consider this vector. This vector is represented by this. Ax is the component along the x-axis, Ay is the component along the y-axis, and these are the unit vectors along the respective axis. This vector in linear algebra, the same vector, this is called algebraic definition, and this is matrix representation, same vector. So in the matrix representation I can represent the vector in terms of its components. What is the components I have? Ax component and Ay components I have for this vector. So this is the matrix we represent. So the same vector can be represented in a different way in a matrix form. Now, but when we have represented this, implicitly we are saying that with respect to ij basis. With respect to ij basis, why we have to say it explicitly ij basis? Because if I can change the basis in a following way, I can change the axis given like this. I just rotate the axis. Vector doesn't change. Vector remains to be same in the space, in the position space or in the problem domain, but I have just rotated the axis, my representation. And if I rotate that, then what will happen? My I would be different. This is now I dash. My j would be different in a different direction, and their components will also be different. But the same wave, the same vector would be represented by different bases, different components with respect to different basis. Right now basis is I dash j dash. Basis is not the same for these two representation, although the vector is the same. The same vector I am representing with two different bases, and if I change the basis, I will change the components as well, and that is why matrix representation will change, but each representation is representing the same vector. Therefore, one can represent the same vector using different bases as long as bases and corresponding components are known. As a physical state in quantum mechanics is represented by a wave function which can be expanded with respect to certain orthonormal bases, the above vectorial argument, the argument which we have given here, applies to quantum mechanical state of a system, and this is called basis set expansion of the wave function. So a wave function, we have seen that in quantum mechanics a wave function can be represented by linear combination of certain function. This is called basis function e to the power I equals 0 to infinity, and I get C naught phi naught plus C1 phi 1 plus like this, just like the representation here with respect to phi basis. What is the difference between these two? Here we have 2-dimensional, but here we have infinite dimensional, because I have infinite number of basis set. So that's the only difference. It's a dimensionality difference, but it's the same idea. I am just with respect to basis, I am representing the wave function, and if I do that, then one can say that this psi x can have a matrix representation, following matrix representation: C0, C1, C2 matrix representation, and this is called the column matrix, which is called vector in linear algebra. We will understand more about it, but the basic connection should be clarified here. A vector and the wave function both would be equivalent in linear algebra in the context of basis set expansion. Here also we have a basis of I and j, and I have expanded this vector and I have got this column matrix. Here I have used different basis I dash j dash, and I am getting a different representation of the same vector. Similarly, here I have components Ci, and this is the basis, and that's why all the components can be collected in a column, and in this column matrix we can represent the wave function. This is the bracket notation we are using, will be using. But one thing we have to remember here, the reason why we can use this basis set expansion is quite clear, because in Hilbert space we said that if in a Hilbert space, if phi are living in Hilbert space, then their linear combination will also stay in Hilbert space, and that's why we can write it. So this representation, basis set representation, is directly coming from the property of the Hilbert space. As long as phi, the basis, are living in the Hilbert space, we can use this kind of linear combination, because linear combination of them would also live in the same Hilbert space. But one thing is clear from this discussion is that the formal mathematical framework of quantum mechanics in the basis set approach represents an infinite dimensional Hilbert space. I told you that this summation is infinite. So dimensionality is going to be infinite dimension. However, no numerical calculation of quantum mechanics can deal with infinite dimensional space. It can only deal with finite dimension of the basis. Therefore, the sum in this equation we have to truncate it to some finite number. Let us say n number of bases we consider. Instead of infinite, we consider n number. And we have to truncate it for the numerical implementation. And this requirement can be fulfilled by making use of reduced Hilbert space. In that case, one would assume that all the general properties of wave functions and the operators which we have discussed so far must be valid in the reduced Hilbert space. Then only we will be able to use linear algebra. So even if I truncate it to some finite value, n number of bases if I use, then we have to assume that even after truncation, the reduced Hilbert space I prepared, this reduced Hilbert space, in this reduced Hilbert space, all the properties which we have seen previously are valid, and there are basically rigorous mathematical support for that. It remains valid. So it's not an issue for the numerical solution to get the numerical solution. So finally, the wave function can be represented in this, and generally we do not mention very frequently, but we should remember that when you say that a function is represented by this column matrix with its components, this can be represented with respect to certain basis, because if the basis is changing, this coefficient will also change, as we have seen here. Two vectors, if the basis is changing, coefficient will change. Similarly, if the bases are changing, coefficient will change, but in the end the wave function will not change. It is just different representation. So when you say that this is the representation of the wave function, we implicitly say that it is with respect to certain basis phi I. We will stop here, and we will continue this module in the next session.